In the previous submodule, we have discussed on blackbody radiation. The most important outcome of Planck's radiation formula was the bold hypothesis that energy is not continuous. Rather, it is discrete. In other words, energy is quantized, and the smallest possible change in energy is h nu, where h was called Planck's constant and nu is the frequency of that light, frequency of the electromagnetic wave. Planck's law was very successful, but still the scientific world was not ready to accept the concept of energy quantization. And believe me, even Max Planck himself did not believe it. The proposition of energy quantization was just an act of despair for him. He was desperate to find out the formula that could explain experimentally observed blackbody radiation spectrum. And out of that desperation, he proposed that concept. Therefore, no one at the time believed the energy quantization, not even Max Planck himself. No one except a nameless, fameless clerk working in a patent office. This man, in 1905, published 4 research papers that revolutionized the world of science and technology followed. Those 4 papers were on the photoelectric effect, Brownian motion, special theory of relativity, and mass energy equivalence. The impact of those work was so great, the year 1905 was regarded as Annus Mirabilis, year of miracles. And hopefully you understand the person is no other than Albert Einstein. He not only believed the concept of energy quantization, but also used the concept in his photoelectric effect. If you remember the photoelectric effect, that only those photons of particular frequency or energy are able to liberate electrons from metal surface. That was the basic concept of photoelectric effect. Now, in the photoelectric effect, Einstein said that light has shown its particle nature. Though we know that in maximum phenomena like reflection, refraction, interference, diffraction, polarization, dispersion, in all these phenomena, light shows its wave nature. We can understand those phenomena by the concept of the wave nature of light or any electromagnetic wave. On the other hand, in case of photoelectric effect, if you only consider the wave nature of light, you cannot understand the mechanism behind it. You need to consider that sometimes light behave as a particle also, and we call the smallest particle of light as photon. According to classical electrodynamics, when an electromagnetic wave passes through a matter, it may be scattered by the electron within the matter. The oscillating electric field of the wave applies periodic force on that electron, which in turn starts oscillating with the same frequency as the incident wave. That means the frequency of the electron remains same as the frequency of the incident electromagnetic wave. Now that oscillating charged electron emits electromagnetic wave of same frequency in all directions. Therefore, the frequency of the scattered wave remained unmodified in comparison to that of the incident wave. So in other words, the wavelength or frequency of the scattered wave is same as the wavelength or frequency of the incident wave. But Arthur H. Compton noticed that whenever a monochromatic beam of X-ray or any other type of wave of smaller wavelength is scattered by a light element like carbon, then the scattered radiation observed along some particular direction consists not only of that unmodified beam, but also of another new modified radiation of slightly longer wavelength, that is shorter frequency. This type of scattering is called Compton scattering, and it cannot be explained by the classical theory. So, whenever an electromagnetic wave of shorter wavelength interacts with a short or small particle like electron, then after the scattering, when the wave is going in a particular direction, and if the wavelength or frequency of that scattered wave is measured, then it is observed that the wavelength of the scattered wave is greater than the wavelength of the incident wave. So in other words, the frequency of the scattered wave is less than the frequency of the incident wave. Now to understand it, we cannot use the normal classical theory. Rather, we need to adopt the particle nature of light. That means we need to think that wave is composed of photons. So if we consider a photon is propagating along this direction and it interacts with a stationary electron at rest, an electron at rest. And after the interaction, after the scattering, if we assume that the photon is going along this direction, say with an angle theta with the incident direction, and the electron goes along a direction phi, then this figure will represent that scattering process. If we assume the frequency of the incident wave as nu, then energy will be h nu and the momentum will be h nu by c. Since the electron is at rest, it has no kinetic energy, so its total energy is just the rest mass energy, that is m dot c square, and its momentum is basically 0. If we assume that the frequency of the scattered wave is nu dash, then its energy will be h nu dash and momentum will be h nu dash by c. And since the recoiled electron is moving with some velocity, its energy can be represented as mc square, whereas momentum as mv. So this table shows the value of energy and momentum of the electron and the photon before and after the scattering process. Now we want to find out whether it is possible theoretically to determine that change in frequency or wavelength. That means whether the frequency or wavelength of the scattered photon is actually different from that of incident photon. If so, then what is that change? What is that shift of wavelength? That we need to determine. And for that, we'll use two conservation laws. One, the energy conservation, and another is the momentum conservation. Therefore, if we consider the conservation of energy, then total energy of the incident photon and the stationary electron is same as the total energy of the scattered photon and the recoiled electron, which can be written as in equation 1. And if we square equation 1, we get equation 2. On the other hand, momentum is a vector quantity. Therefore, if we want to use the conservation of momentum, we need to use it along two mutually perpendicular direction x and y axis. Therefore, this is the conservation of momentum along x, and this is the conservation of momentum along y-axis. Since it is assumed that this is the initial direction of approach, and this is the direction along which the photon propagates with an angle theta. So if this is your momentum of the photon after the scattering, that is h nu dash by c, then along x-axis we have only the component h nu dash by c cos theta. This is cos theta component of the momentum along x-axis and sin theta component along y-axis. On the other hand, since the recoiled electron goes along a direction phi, therefore, if his momentum is mv along this direction, then the mv cos phi will be the contribution of momentum of the recoiled electron along x-axis and minus mv sin phi along y-axis. So we have so many quantities here: nu dash, theta, phi, mv. Now we are only interested in photons. That is, we are interested in the relation between the frequency or wavelength of the scattered and incident photon. So we need to observe nu dash, and theta. So we actually want to get rid of this phi. And that's why we have written this conservation of momentum along x and y axis as per equation 3a and 3b. So that if we square 3a and 3b and then add them, then we can get rid of this phi. So our equation becomes like this. And if we use this equation obtained from conservation of momentum along with that obtained from conservation of energy, then with some simplification, we can get 1 by nu dash minus 1 by nu equals to some value. So we observe here h is the Planck's constant, has a value, maybe it's very small, but has a positive value. M dot rest mass of electron, c square. So all this quantity outside the bracket contributes to some amount of value. And therefore, only in case of theta equals to 0 degree, the left hand side, that is 1 by nu dash minus 1 by nu, is not equal to 0. Therefore, the point is the frequency of the scattered photon is not same as that of incident photon in general. If we want to represent it in terms of wavelength, then we get lambda dash minus lambda, that is change or shift in wavelength, equals to h by m dot c 1 minus cos theta. Now, if we say this quantity h by m dot c as Compton wavelength, because it has the dimension of wavelength, then delta lambda can be written as lambda c into 1 minus cos theta. This lambda c, Compton wavelength, is a characteristic of any particle. And for electron, this value of Compton wavelength is 0.02427 angstrom. Different particles have different value of Compton wavelength. And from the expression of delta lambda equals to, or Compton shift equals to lambda c 1 minus cos theta, for a particular particle, like say electron, lambda c is constant. Therefore, delta lambda, the Compton shift, depends only on the angle of scattering theta. It only depends on scattering angle theta. If theta is 0, then delta lambda is 0, that is the minimum possible value. If theta equals to 90 degree, then Compton shift is equal to Compton wavelength. On the other hand, when theta equals to 180 degree, we get maximum Compton shift, which is twice of Compton wavelength. Now, one point is to be noted that sometimes when the scattering occurs, then instead of the electron, the atom may interact. If the electron is bound to the atom, then the whole atom takes part in that scattering process. And in that case, delta lambda will be h by mc 1 minus cos theta. Instead of mass of electron, now the mass of the whole atom needs to be considered. And generally, the mass of the atom is 10 to the power 4 times larger than that of an electron. Therefore, the Compton shift becomes 10 to the power minus 4 times smaller when the whole atom takes part in that process. And hopefully you understand, in case of electron, already the value is very small. The Compton wavelength, that is h by m dot c for electron, is already very small. Now, for the atom, it will be much, much smaller, because lambda c will be then 0.02427 into 10 to the power minus 4 times. That means it will be very, very small, and it is so small that it is hardly detected by any sophisticated instrument present nowadays. So, one point we need to understand that instead of X-ray, if we use any visible light, then Compton scattering occurs. Compton scattering occurs, but the change in wavelength in comparison to the incident wavelength is so small that it is hardly detected by the instrument. Or when the atom takes part in that process, then also Compton scattering occurs. But the scattering value, that means delta lambda, is so small, it is hardly detected by that instrument. If we observe the actual experiment by Compton, where K alpha X-ray was utilized, whose wavelength is 0.709 angstrom. And when the scattered wave was observed from different angle of scattering, like 0 degree, then as per the formula, delta lambda equals to lambda c 1 minus cos theta, when theta is 0, then there is no Compton shift. But when the scattering angle is increased from theta to say 45 degree, then delta lambda gives some value. So that lambda dash, which is equals to lambda plus delta lambda, becomes 0.715 angstrom. 0.715 angstrom from 0.709 angstrom. So now for the angle 45 degree, two waves are observed. Two peaks are observed at two different wavelengths. The first one, 0.709 angstrom, is the unmodified line, because wavelength is not changed, wavelength is not modified, so it is an unmodified line which occurs when that incident photon interacts with the whole atom. Whereas when the incident photon interacts with an electron, then as per the formula given by Compton, delta lambda gives a value, and as a result, lambda dash increases from the value of lambda. And if the scattering angle increases to say 90 degree, 135 degree, etc., then that Compton shift increases more and more. Compton shift delta lambda increases, and in all these cases we get modified lines. We get modified lines along with the unmodified line. So remember that though in Compton effect, if we want to observe this shift, if we want to measure this shift, if we want to detect that shift, then we need to use a particular type of wave. That means we should use a wave with smaller wavelength. Otherwise, it's hardly detected, because our instrument has not that accuracy that it can measure 6000 angstrom and 6000.001 angstrom simultaneously. Or in case of interaction with the atom, the change is so small, the shift is so small, it is hardly detected by any subsequent instrument. So if we do some numericals, let's say an X-ray of wavelength 0.2 angstrom is scattered by a stationary particle. It's not electron. A stationary particle, it's not mentioned whether it is electron or not. A stationary particle of Compton wavelength 2.43 angstrom at an angle 45 degree. So what we have given is now incident photons wavelength supplied 0.2 angstrom, angle of scattering 45 degree, and Compton wavelength of that particle is also given. Therefore, from the Compton scattering formula, we can estimate that Compton shift delta lambda from the formula of lambda c 1 minus cos theta. Lambda c is given as 2.43 picometer, that is 0.0243 angstrom. Theta is 45 degree. If we put those values, Compton shift is estimated, and therefore the wavelength of the scattered photon can also be estimated as this. So we observe that from 0.2, the wavelength increases to 0.2071 angstrom and scattering angle of 45 degree. Now, if we want to estimate the energy gained by that recoiled electron, how will you do that? We can use some mathematical formula for that, but we don't require. Now we observe that initially the electron was at rest, but after the scattering process, electron is moving with some velocity. That means it has gained some kinetic energy. Who has supplied that kinetic energy to the electron? Electron got that kinetic energy from the photon only, because these are the two particles that interact with each other. So whatever energy the electron got, that must be from the photon itself. That means whatever energy the photon losses, that must be gained by the recoiled electron. And we know the initial energy of the photon is h nu, and After the scattering process, the energy of the photon is h nu dash. Therefore, the photon loses this amount of energy, h nu minus h nu dash. So that must be the energy gained by the electron as its kinetic energy. So the kinetic energy of the electron must be h nu minus h nu dash, or in terms of wavelength, since wavelength is supplied here, you can write it as hc by lambda minus hc by lambda dash. hc can be taken common, so it is 1 by lambda minus 1 by lambda dash. Now all the quantities present here are either given or estimated. So hc, the two constant, Planck constant, and velocity of light in free space, we know. Lambda is given as 0.2 angstrom and lambda dash is estimated to be 0.2071 angstrom. So if we put those values, the kinetic energy comes out to be 3.41 into 10 to the minus 16 joule. The value is so small in joule that we can write it in terms of electron volt. So our final answer comes out to be 2.13 kilo electron volt. From joule to electron volt, we can convert by the charge of the electron. Similarly, in this problem, it is said that molybdenum K alpha X-ray of wavelength 0.711 angstrom are allowed to suffer Compton scattering from a carbon target. Calculate the wavelength of the photon scattered at an angle 45 degree. Also estimate the kinetic energy of the recoiled electron. So here the Compton wavelength is not supplied. That means we can assume that the photon interacts with an electron and Compton wavelength of the electron is known, 0.02427 angstrom. Therefore, the process will be same. We can estimate the wavelength of the scattered photon as lambda dash equal to lambda, that is the wavelength of the initial photon, which is given, plus lambda c 1 minus cos theta. So if we put those values, lambda is 0.711, lambda c for electron 0.02427 angstrom, and theta as 45 degree, we get lambda dash as 0.718 angstrom. For the estimation of kinetic energy, same process can be followed. That means kinetic energy will be hc by lambda minus hc by lambda dash, that is whatever energy lost by the photon must be gained by the recoiled electron as its kinetic energy. We put those values, we get kinetic energy as 170.3 electron volt. In the last problem, it says that a radiation of wavelength 0.712 angstrom suffers Compton scattering in carbon. Okay. Find the wavelength shift of photon scattered at 90 degree if it is scattered by the whole carbon atom. Now the whole carbon atom expert in that scattering process. Therefore, though the process remains same, that means initial wavelength we know, angle of scattering we know. Now delta lambda is h by mc 1 minus cos theta. Instead of m naught, I am writing m because now it is not the electron who is taking part in that scattering process, but the whole atom. So its mass must be different from the mass of electron. Now what would be the mass of the carbon atom? We know that in case of carbon, there are 6 electrons, 6 protons, and 6 neutrons. Therefore, then in the nucleus, there are 12 particles, 6 protons and 6 neutrons. And the masses of proton and neutrons are almost same. We can assume that the mass is 1.67 into 10 to the power minus 27 kg. Therefore, the quantity within bracket is the total mass of the nucleus. And total mass of the electron will be 6 into 9.11 into 10 to the power minus 31 kg. Now you observe this mass of electrons, mass of all the electrons is negligible in comparison to the mass of the nucleus. So you can keep it or you may neglect it also. So that delta lambda becomes, so all the quantities are known now, so delta lambda becomes 1.1 into 10 to the minus 16 meter, that is 1.1 to 10 to the power minus 6 angstrom. You observe the shift is so small, that's why it is hardly detected by any sophisticated instrument also.